Effective antenna aperture, often called effective area and denoted as A suffix E, is a measure of how successfully an antenna captures radio frequency energy from a passing electromagnetic wave. Think of an antenna as a rain catcher in a storm. The larger the funnel's opening, the more water it collects. Similarly, the larger an antenna's effective aperture, the more RF power it can extract from an incoming signal and deliver to a receiver. An antenna's effective aperture is directly tied to its gain and the wavelength of the signal it is receiving. The relationship is defined by the formula AE is equal to lambda squared by 4 pi the whole multiplied by G, where AE is the effective aperture, typically in square meters, lambda is the wavelength of the RF signal, G is the linear gain of the antenna, not in decibels. This equation reveals a crucial role in electromagnetics. To maintain the same amount of gain at lower frequencies, longer wavelengths, the antenna must have a proportionally larger effective aperture. It is easy to confuse an antenna's physical size with its effective aperture, but they are not always the same. For antennas with solid physical surfaces like a parabolic satellite dish or a horn antenna, the effective aperture is closely related to the actual physical area of the dish opening, A physical. However, no antenna is 100% efficient at capturing energy due to surface imperfections, feed blockage, and edge tapering. This introduces aperture efficiency, epsilon A, a percentage that bridges the gap between physical and effective size. AE is equal to epsilon A into A physical. Most parabolic dishes have an aperture efficiency between 50% and 70%. Because wavelength lambda is squared in the gain denominator, doubling the frequency of your signal will quadruple the gain of a dish antenna, assuming its physical aperture remains constant. G is equal to 4 pi AE all divided by lambda squared. For wire antennas like dipoles or monopoles, the physical area is essentially zero, just the thickness of the wire, yet they still capture RF energy. Here the effective aperture bears no visual relation to the wire's physical footprint. Instead, it describes an invisible capture zone surrounding the wire from which it draws power. For a standard half-wave dipole, this capture area is roughly oval-shaped and extends significantly beyond the wire itself.